Okay, so today I want to do a review for the third test on chapter 9, and get this set up. Okie dokie, so this is like test 3. Test 3 review, and 9.1 is kind of an intro section, so 9.2, we're looking at problems like 11, 23 odd, 29 to 57 odd. And basically that's going to be geometric series as well as the telescoping series. Okay, and then maybe nth term test, which is actually 9.1, but some of the exercises in 9.2 use the nth term test. Okay, so basically number 15, the directions are to determine if it converges or diverges. And we have the series n equals 1 to infinity of n cubed plus 1 all over n cubed plus n squared. Okay, so this is clearly not geometric. It's clearly not telescoping because the degree of the denominator is cubed. The telescoping will have a quadratic in the denominator and a constant in the numerator. So the only test you have to kind of work with then is the nth term test. So we'll say note or by nth term test. And you kind of have to write stuff out. I know on WebAssign you're just, does it diverge or does it converge? And it's kind of silly. Just keep in mind you're talking to another human on this test. And so you'll have to show some work. Okay, so by the nth term test, we have the limit of n cubed plus 1 all over n cubed plus n squared as n goes to infinity is just equal to the ratio of the high degree terms. Okay, so n going to infinity. You could do that when you have polynomials in the numerator and denominator both going to infinity. N cubed over n cubed is just 1, so we have the limit of n going to infinity of 1, which is equal to 1, which is not 0. Okay, and our nth term test said that if the limit of the terms of the series is not equal to 0, then the series diverges. So thus, the series diverges. Okay. So you can't just flip a coin, right? You can't just write diverge or converge. I'm going to mark that wrong. Okay, and you're not going to get any credit. You have to write out what you're doing. If you did an nth term test, you have to show me the limit. So you have to show me the limit, and then you also have to make your conclusion. And you have to tell me what test you're using. So tell me the test, show the test, and then make your conclusion. Okay. All right, so let's try number 33, where they want us to find the sum of the series. So 8 plus 6 plus 9 halves plus 37 eighths. This guy is a geometric series. Plus dot, dot, dot. So our formula for the sum of a geometric series is the sum AR to the n from n equals 0 to infinity equals a over 1 minus r, assuming that r is less than 1. The absolute value of r is less than 1. Okay, so here we need to figure out the r value. And to get the r value, you just take the ratio of two consecutive terms. So from above there, you could consider 9 halves and 6. Okay. So 9 halves divided by 6 is the same as 9 halves times 1 over 6. So we can remove 3's there, and we end up with r equaling 3/4. For a, I note that when n is 0, I need ar to the 0 to equal the first term of my series, this guy. Okay. So AR to the 0 should equal 8. In other words, A must equal 8. Okay. So all of this material, then we substitute into our formula. So in our case, we have the sum from n equals 0 to infinity of 8 times 3/4 to the n. And so our answer will be 8 all over 1 minus 3/4 which is 8 times 4, right? And that will be 32. Okay. So again, there's work to show. You can't just write 32. I'm going to be wondering what you did. Okay. Okay, let's try number 38. And again, we're looking for the sum of the series. And I have the series n equals 1 to infinity of 1 all over 9n squared plus 3n minus 2. Okay, in this case, it has a quadratic in the bottom and just a constant up top. So it's probably telescoping. So we're going to want to do a partial fraction decomposition on this fraction. Let's factor the denominator. That'll be 3n and 3n, and then 2 and 1. We want the bigger one to be positive and the smaller one to be negative. Okay, so we have a all over 3n minus 1 plus b all over 3n plus 2. Okay, multiply through and we get 1 equals a times 3n plus 2 plus b times 3n minus 1. And then we do our substitutions, so let's let n equal negative 2/3 first off. So the a part will be 0, and then we have b times negative 2/3 times 3 is negative 2, and then minus 1. So we'll get negative 3b equal to 1, and that tells me b is negative 1/3. Okay. And try n equals, I guess, 1/3. So 1 will equal a times 3 times 1/3 is 1, and then plus 2, and then the b part will be 0. So I'll get 1 equals 3a. In other words, a equals 1/3. Okay. So we can use that to rewrite our sum above as, and we want to turn it into a limit. So limit as n goes to infinity of the sum from, and I guess I got myself into trouble with my index variable. So I'm just going to change it to k or something. So we'll go from n equals 1 to k of, what do we have, 1/3 all over 3n minus 1 minus 1/3 all over 3n plus 2. Okay, and we want to expand that thing and take its limit. Because the summation is now finite, you can factor the 1/3 out, and you'll have the limit as k goes to infinity of 1/3 times this telescoping sum. Right? So let's write out the sum. So I start with n equals 1. So I'll have, so I'm plugging n equals 1 into this formula that I'm going to underline in blue. Okay, this formula here, except without the 1/3 because I factored it out. Okay, so I have n equals 1, so 3 times 1 is 3, minus 1 is 2, and then minus 1 all over 3 times 1 is 3, plus 2 is 5. Okay, and then plus, now I plug in n is 2, so 6 minus 1 is 5, minus 1 all over 6, 7, 8. Okay, and then plus, try n is 3. In this case, we get 1 all over 8 minus 1 all over 11. Okay, and then on and on and on. Usually you just want 3 or 4 terms so you can see nice cancellation if it exists. On and on and on. And then let's do like the last 3. So n equals k minus 2. Will be 1 all over 3k minus 6 minus 1, so that's 3k minus 7, minus 1 all over 3k minus 6 plus 2, so that's 3k minus 4, and then plus n equals k minus 1, so it'll be 1 all over 3k minus 3 minus 1, so 3k minus 4, and then minus 1 all over 3k minus 3 plus 2 is just 3k minus 1. And then plus the last guy, which is n equals k, which will be 1 all over 3k minus 1 minus 1 all over 3k plus 2. Okay. So in this case, we got a real nice cancellation. It's not always that nice, but here just like everything cancels all the way up to the last term. So our limit will become, the limit as k goes to infinity of 1/3 times 1/2 minus 1 all over 3k plus 2, or 3k plus 2. All of this n stuff, no matter what it is, it's going to go to 0 because it's basically, it has a polynomial of degree 1 in the denominator and degree 0 in the numerator. So it's going to go to 0. So you can bet, anything in that second part of the sum with all the k stuff is going to just be 0. And you'll always just be left with kind of the constants from the first part, which I'll sort of box in red. Okay, so it's basically this stuff. You find the cancellations there, and what's left over is going to be the limit, kind of, right? We still have to worry about the 1/3, but in our case, the only thing left over was that 1/2, right? So that's kind of our answer, but you still need to multiply it by 1/3. Okay, so 1/3 times 1/2 is 1/6, and that would be our answer in this case. Okay, so you need to show the work. You need to show that big red box thing that I just drew out to show that you're actually doing the work. You need to show the partial fractions if you have to. I expect you to be able, so, there's certain things, there's no way you did them in your head, right? Unless you're like the next Goodwill Hunting. And if you are like that smart, you probably shouldn't be at Tri-C unless you just love the people here. Go off to MIT or something like that and get in there with those folks if you're that good. And you could talk to me and I can tell you some people to talk to, okay, if you're that good. Okay, so 9.3 anyways, moving on. 9.3, I'm looking at problems like 3 to 21 odd, and then 29 to 37 odd, and then 69 to 79 odd. And here we want to do the integral test and some p-series stuff. So for the integral test, you kind of have to confirm like 3 things, right? It's positive, continuous, and decreasing. And then you can do the integral test. So in general, what I'll do is let you assume it's positive and continuous. Okay, so on my test, I'll say assume it's positive and continuous and show it's decreasing. So how do I show it's decreasing? So this is before you can actually do the integral test. Let's look at number 15, where we have the sum of the ln of n all over n squared, okay, from n equals 1 to infinity. So what you need to do is to consider its kind of sister function on the real numbers. So consider f of x equals ln x over x squared. And what you need to do is take its derivative and show it's negative on the given interval. And what is the interval? The interval is going from 1 to infinity. It's from the limits on the summation. Okay? So I need to consider this function on the interval from 1 to infinity and show that the derivative is always negative there. Okay? So we note f prime of x is equal to low times the derivative of the high minus the high times the derivative of the low all over the low squared, x to the 4th. Okay. If we simplify, you'll get x minus 2x ln x all over x to the 4th. The denominator is always positive because x to the 4th, anything you put in there, especially in this interval from 1 to infinity, is going to be positive. So the only question is this x minus 2x ln x. And this is something, one of the reasons why I wanted to do this problem was to kind of, deal with this issue. note for x greater than 1, we have that x is less than x ln x. And if you do computer programming and you're talking about big O, big theta, big omega notation, this is kind of a fact of life. Okay, so for x greater than 1, x is less than 2x ln x. Okay, or it's greater than or equal to if you want to just include the entire domain from 1 to infinity. So at 1, 1 will be less than or equal to 1 times the ln of 1. ln of 1 is, so that wouldn't work in that case. So you need it to be strictly greater than. Okay, ln of 1 is 0. So we need x to be greater than 1. Okay, so that's a little hitch in our plans. We'll have to push out the interval to be 2 to infinity or something like that. So this interval needs to be adjusted for this to work. Anyways, well, maybe not. Maybe we don't even have to worry about that because look, if you're given that x is less than or equal to x ln of x, you can certainly say in this interval that x ln of x is less than 2x ln x's. Okay. Would that be true? No, you still need x greater than 1 to pull that off. And anyways, this factoid is from computer science, right? So this is something that's probably not as obvious to you, but computer science people are like, oh yeah, I remember that. But if you have this fact holding, then you can work with the inequality x less than 2x ln x, and then subtract 2x ln x to the other side. And you'll have that inequality. And what does that tell you? Well, it tells you the numerator is less than 0. In other words, you have a negative over a positive for x greater than 1. In other words, this thing will be less than 0 in that interval, and therefore the derivative is negative, and therefore the function is decreasing. Okay, so this implies f of x is decreasing. Okay, so that one's a little harder. I wouldn't put that one on the test because I wouldn't expect everybody to be familiar with that kind of work. But I would put an easier one on the test, right? So I'll let you assume it's positive and continuous, and you just have to show it's decreasing. So you have to take the derivative, and you have to show this inequality. You have to say, oh, the derivative is less than 0. And usually it'll be obvious. You could just, the numerator is negative, the denominator is positive, therefore it's decreasing. Therefore, we can use the integral test. Okay? So once you've concluded that, now we go to our integral test. In particular, technically we should start at 2 to infinity, so we know the function is decreasing, but I'm going to start at 1 to infinity because it'll have the same results. Okay? Just ln of x all over x squared dx then. Okay? And by parts, we can do by parts here. So u is going to be ln of x, and dv will be x to the negative 2. So v will be negative x to the negative 1, and then du is x to the negative 1. So this will be, and you'd have to do the limit as b goes to infinity. We'll get there. But anyways, this is negative ln x all over x minus negative, so it'll be plus integral of x to the negative 2 dx. And then that thing will equal, let me box this off, that will equal negative ln of x all over x minus 1 over x. And we have to remember to evaluate from 1 to infinity. So let's change it into a limit, right? So we got a limit as b goes to infinity of this mess. So we got negative ln of b all over b minus 1 over b minus negative ln of 1 is 0 minus 1 over 1. Okay. Then I have to take the limit of this thing. So this first term may not be clear, but you could do L'Hopital's on it. So the limit as b goes to infinity of negative ln of b over b, if you do L'Hopital's, because it is infinity over infinity type, we'll have negative 1 over b over 1, which will go to 0. Okay, so if it's not clear, hopefully that just made it clear that this thing is going to 0. This guy is clearly going to 0. It's just 1 over b as b goes to infinity. And you're just left with minus negative 1, which is equal to 1. So if that's convergent, it implies the original series converges. Okay, so hence the series converges. Okay, so you have to show work. So number one, you're going to have to show that the function is decreasing. That means take its derivative and show me it's negative. Okay, so you should be making this statement right here. Okay. I don't even need you to almost don't even need you to explain it. Just literally find the derivative and write it's less than 0. And then after you get that, you have to go and do your integral. Okay, and the integral is improper, which means there's work to be done, and you have to go through the entire thing. Don't just write divergent or convergent. I'm not going to give you credit. Okay, so you have to go through the whole process. Okay. Then we have stuff on p-series, so let's look at number 35. So determine if it's convergent or divergent. 2 plus 1 over 3 root 3 plus da da da. The trick to this is to rewrite it as in series form. So this is 1 all over n root n, where n is going from 1 to infinity. And that's a p-series. Okay, so it's n equals 1 to infinity of 1 all over n to the first times n to the 1/2, which is n to the 3/2, which is a p-series where p equals 3/2, which is greater than 1, which implies it's convergent. Okay. Well, okay. Not much work to be shown there, but I mean, there is some work, right? So I had to note what kind of p-series it is, say whether it's convergent or divergent, and there was this step going from here to here. Okay? So if you're not showing work, I'm going to be really worried. I'm going to be like, is this person trying to pull a fast one on me? You know, I'm getting older, but I don't know, right? You don't want to be in that category of humans where I'm wondering whether or not you're doing your job. Anyways, 9.4, these are always the harder ones for me, using the direct comparison test. I tried to make it as simple as possible for you doing your answer. So there's like 3 steps to show. So number 15, let's look at this guy. N equals 0 to infinity of sine squared n all over n cubed. So first you have to do an inequality, right? If you're trying to show that something is convergent, you want to bound it above by something known that converges. Okay, so in this case, looks like sine squared is always less than 1 all over n cubed. And we know about that series 1 over n cubed. Okay, so that series is a p-series where p equals 3 and it's convergent. Right? So step 1, for this to work, the guy above has to be convergent to prove that the original series is convergent. So it has to be less than. If it's not less than, you're out of luck. And of course, this is less than just because sine is always less than 1. Right? So the numerator is less than 1, so clearly it's less than. So step 2 is always making a statement about the series you're comparing it to. Okay, so you need to tell me what kind of series it is and whether it converges or diverges. And then step 3, you make your conclusion. So hence both converge. Okay. For the limit comparison test, I kind of want you also to be showing me 3 steps. So use limit comparison. So first, what number is this? It's 23. And we get given the series 1 all over n times the square root of n squared plus 1. So again, first, I'm going to give you 3 steps. Okay, so first step, I want you to talk about the series you're comparing it to. And usually to get that, you just kind of chop off all the constant stuff and work with the big stuff. So my series I'm going to compare it to is the series of 1 all over n times the square root of n squared. And for n greater than 1, the square root of n squared is just n. So this is the same as 1 all over n times n, which is n squared, which is what? You tell me whether it's convergent or divergent, and you tell me what kind of series it is. Again, it's a p series. P equals 2, and it's convergent. Okay. Okay. Then step 2, I need to do my test, right? So I need to take the limit of the ratio of these things. So 1 all over n square root of n squared plus 1 all over 1 over n squared as n goes to infinity. Taking reciprocals and multiplying out, that will be n squared all over n times the square root of n squared plus 1. You can simplify that. That's the limit as n goes to infinity of n all over the square root of n squared plus 1. And then you could take the limit of that thing again by kind of just cutting off the high degree terms in the numerator and denominator. You'll get n all over the square root of n squared. The square root of n squared is absolute value of n, but when n is going to infinity, we can just pretend it's n. Okay, so we have the limit as n goes to infinity of n all over n. In other words, that's just the limit of 1, and the limit of a constant is just the constant. Okay. Okay, so if this number is greater than 0 and finite, the two series have the same behavior. So thirdly, make your conclusion, and here both converge. Okay, so hopefully that's clear. 3 steps. First, tell me the series you're going to compare it to. Tell me whether the series converges or diverges, what kind of series it is. Secondly, do the test. And then thirdly, make your conclusion. Okay. So let's go on now to 9.5, and we're looking at 9 to the 25 odd, and these are alternating series tests, so determine if the thing is convergent or divergent using the alternating series test. Let's look at 25. We have -1 to the n plus 1 times the square root of n all over n plus 2. So there are 2 steps. The first step is to take the limit of a sub n, which in this case is square root of n all over n plus 2. So it goes to infinity. And then we could do the trick where we just take the high degree terms and take the limit of that. So that's the limit as n goes to infinity of square root of n over n is the same as 1 over square root of n for these positive n values. And then this will be the limit, that'll just be 0. Right, so that'll just go to 0. So, and that's what we want. We want the limit to go to 0, and secondly, we want to show it's decreasing. Okay, so I gave you algebraic tests for this. Usually, I just do a ratio of the terms of the series and show that that's less than or equal to 1. Okay, but in this case, if you look at the thing you got, it's not going to be obvious, right? So if you tried that, you would get the square root of n plus 1 all over n plus 3 times n plus 2 all over the square root of n. So there's kind of a fight going on. It's like, right, I can see from this it's less than 1, but from this part of it, it's kind of greater than 1. So it's not clear whether or not that's really less than or equal to 1. Okay, I would be skeptical unless I had somebody really convince me otherwise. So what I'm going to do in this case, I'm going to take the derivative. I'm going to look like I did with the integral test. I'm going to consider its sister function, f of x equals square root of x all over x plus 2. Take its derivative, f prime of x is going to be low times the derivative of the high minus high times the derivative of the low, which is just 1, all over x plus 2 squared. And then I'm going to clean it up, multiply top and bottom by 2 square root x. And what do we get? X plus 2 minus 2x all over 2, sorry, my pen is acting up on me, 2 square root x times x plus 2 squared. And so that will be equal to negative x plus 2 all over 2 square root of x times x plus 2 squared, which will be less than 0 for x greater than 2, right? Because that denominator is positive, excuse me, for all x values greater than 2. But the numerator will be negative because once you get negative x, once you get x bigger than 2, negative x will be plus 2 will be negative. Right, so that shows that this the terms of the series are decreasing, and therefore both of these facts hold, and therefore by the alternating series test the series is convergent. Okay, so you really need to show me both set of facts in order to pull this off, and you notice in this case it was not clear. Okay, so if something is not clear, don't expect me to be convinced. Okay, I'm getting older, I'm thick in the head. If you don't make it obvious for me, it's like, no. Okay, you gotta make it obvious, otherwise I'll think you're just fishing. Okay, so 9.6, now we get to the ratio test, one of my favorite tests. So 17 to 35 odd, and then we go 53 to 67 odd. And let's take a look. So use the ratio test to find whether or not the series converges. I'm going n equals 0 to infinity, negative 1 to the n, 2 to the n, all over n factorial. Okay. So when I work with this thing, the factorials, I usually work with the recursive definition, right? So 5 factorial is really equal to 5 times 4 times 3 times 2 times 1. And you look there, hey, 4 factorial is inside of 5 factorial. 5 factorial is really 5 times 4 factorial. So whenever you see it like an n factorial, you can always write it as n times 1 less than that original thing, n minus 1 factorial, right? Okay, one other factoid is that the absolute value of negative 1 to the n is just going to be 1. So you can always just kind of kick those out of your limits and not even worry about them, okay? So the limit as n goes to infinity of the absolute value of the ratio of this thing, I'm not going to worry about that negative 1. Okay? I just put it in the trash. I'll have 2 to the n plus 1 all over n plus 1 factorial times n factorial all over 2 to the n. You'll notice at this point it's not even necessary to have the absolute values. The absolute values really only become important when we're doing the radius of convergence later on, right? Okay, so anyways, here we go. Limit as n goes to infinity of 2 to the n plus 1 over 2 to the n. That's from our exponent rules. Okay, so x to the m all over x to the n is equal to x to the m minus n. Right, so 2 to the n plus 1 minus 2 to the n plus 1 all over 2 to the n is 2 to the n plus 1 minus n, which is just 2 to the 1. So we get 2 times n factorial, and then I use the recursive definition for factorials in the denominator. So it'll be n plus 1 times n factorial. In other words, if my pen would work, n plus 1 times n plus 1 minus 1 factorial. N plus 1 minus 1 is just n. So I'll have n plus 1 times n factorial, and then you see, oh, those n factorials will cancel, and I'm left with the limit as n goes to infinity of 2 all over n plus 1, which we all know goes to 0, which is going to imply that the series is absolutely convergent. You just have to remember the criteria. You probably want to write out all the tests you're doing and all the criteria on a piece of paper so you have it there so you can reference it. It's also, there's one in the book. If you want like a nice reference sheet, I usually have students memorize it, but it's a little hard to grade people on memorization tasks here. So if you want that sheet, I usually make them memorize. You can email me, I'll send it to you. Okay, so anyways, there's that. 9.7 now, we're talking about Maclaurin polynomials, 17 to 31 odd. Number 20, we want to build a Maclaurin polynomial for f of x equals cosine pi x, n equals 4. Okay, so here we go. I need the first 4 derivatives. So f of x is cosine pi x. F prime of x, it's been so long since we've done derivatives, right? So negative sine of pi x, but then with the chain rule, I have to multiply by pi, right? So f double prime of x is negative pi cosine pi x, but then I have to multiply by another pi, so that's negative pi squared. The third derivative, now negative times a negative, because the derivative of cosine is negative sine, so it would be positive pi, and then there'll be another pi because of the chain rule. And then finally, the fourth derivative will be pi to the fourth cosine pi x. And then I have to evaluate these at 0 because it's Maclaurin. Cosine of 0 is 1. So it's cosine of pi times 0. Pi times 0 is 0. Cosine of 0 is 1. Okay. F prime of 0 will be 0. Sine of 0 is 0. F double prime of 0 will just be the negative pi squared. F triple prime of 0 will be 0. And then the fourth derivative evaluated at 0, pi to the fourth. And then we just put it into our formula for the Maclaurin polynomial degree 4. Whoops. And what do we got going there? So P4 of x will be 1 plus 0x minus pi squared all over 2 factorial x squared plus 0 x cubed over 3 factorial plus pi to the fourth all over 4 factorial x to the fourth. Okay, 9.8, we get the radius of convergence stuff. And we use ratio test to determine the radius of convergence. Okay. Expect 1 or 2 of these, and I will expect to have ones on there where you're actually having to go after the endpoints. So 25, series n equals 1 to infinity of negative 1 to the n plus 1 times x minus 4 to the n all over n9 to the n. Okay, so I do the limit as n goes to infinity of the absolute value. Again, you can throw the negative 1 in the trash and then just worry about x minus 4 to the n plus 1 all over n plus 1 times 9 to the n plus 1 times n times 9 to the n all over x minus 4 to the n. Okay, exponent rolls all over the place. So you're subtracting exponents when you do division. That will result in 1 factor of x minus 4 in the numerator. And the denominator will have 1 factor of 9. And then there will be an n all over an n plus 1. We can factor out anything not dependent, we can factor any factors not dependent on n out of the integral, and we have to keep the absolute value attached to it. So absolute value x minus 4, we could also factor out the absolute value of 1/9, which is 1/9. The absolute value of 1/9 is 1/9. Okay, so you don't need the absolute value on the 9. And then we have the limit of n all over n plus 1. I don't need the absolute value there anymore either. The limit of n over n plus 1, again, you can do this trick with polynomial limits. That will just be 1. So you'll be left with x minus 4 all over 9. And we know this thing converges absolutely when that row value, which is this limit, is less than 1. Okay, so we can get kind of our radius of convergence. Okay, so we'll have x minus 4 over 9 less than 1 greater than negative 1, which will imply negative 9 is less than x minus 4, which is less than 9, which will imply negative 5 is less than x is less than 13. Okay, so the series will be absolutely convergent in that interval. We still have to worry about the endpoints though, right? So we'll look at x equals negative 5, and we literally plug negative 5 into the original series up here. So when I plug -5 into x, -5 minus 4 is -9. Okay, so what do we have? In that case, we have the series of -1 to the n plus 1 times -9 to the n all over n times 9 to the n. Okay, we got to be a little careful about how we simplify this. This is exponents rules all over the place. -9 to the n. So -9 to the n is equal to -1 times 9 to the n. Right? And then we could distribute that exponents and get -1 to the n times 9 to the n. Right? So that's what I'll have, -1 to the n times 9 to the n, and then I can remove the 9's to the n's in the numerator and denominator. -1 to the n plus 1 times -1 to the n. What is that? Well, you add the exponents, you get -1 to the n plus 1 plus n, which is 2n plus 1. And then you could factor that, -1 into -1 to the 2n times -1 to the 1. -1 to the 2n is -1 squared to the n. Okay. -1 squared is 1, and 1 to any power is 1. So at the end of the day, what this thing equals is just -1, believe it or not. Okay. Okay, so we're getting the sum of the 9's cancel. This part of it is this right here, so that's just -1. And then all over n. And what the heck is that? Well, that's just a constant multiple of the divergent harmonic series, which is also divergent. Okay. So multiplying series by a constant will not change its behavior, right? Adding a couple terms or subtracting a couple terms from a series also will not change its behavior. So this guy right here is divergent. It's a constant multiple of the harmonic series, but it's still divergent. Right? Okay, let's look at the other endpoint, 13. And now I plug 13 into the original series. So looking back at the original series, where that arrow is, I'm plugging 13 in there. So it'll be 13 minus 4, which is 9. Okay, so my series will be -1 to the n plus 1 times 9 to the n all over n, 9 to the n, which will equal the series, this time's a lot easier, -1 to the n plus 1 all over n. Okay. This is an alternating series, so I have to do alternating series test. So note, alternating series test. So first, the limit of 1 over n is 0, and then secondly, the ratio of a sub n plus 1 and a sub n is n all over n plus 1, which is definitely less than 1, so therefore it's decreasing, and therefore these two things imply it's convergent. It's the alternating harmonic series. Okay, folks? Okay, so at the end of the day, the interval of convergence, I'll just call that IOC, is going to be -5 to 13, including 13. Okay, so some takeaways. What do I need you to show? Well, I need you to show the limit, the ratio test there. You should be showing me you finding the radius of convergence, this interval here. Then you should be checking the endpoints. So you should be substituting in the endpoints, looking at those series, and then making conclusions about those series. Not just saying, ooh, it diverges, or ooh, it converges. You should be showing me evidence as to why it converges or diverges. Okay? So I need to see work, not just a flip of a coin. Okay. 9.10 then is the grand finale, and that's working with the Maclaurin and Taylor series. We're looking at problems like 5 to 15 odd, 27 to 39 odd, and then 63 to 67 odd. Okay. Okay, so for example, number 11, we're tasked with finding a Maclaurin series for the ln of x. Actually, this is a Taylor series. We have c equals 1. Okay, so in this case, I'll ask you to show maybe the first 6 terms of the series, or first 5 terms. Okay, so show me the first 5 terms of the Taylor series. Okay, so again, I'm going to need derivatives, right? So f of x is ln x. I need to go up to the fifth derivative because I need 5 terms, right? F prime of x is 1 over x, which is x to the negative 1. F double prime of x, negative 1 times x to the negative 2. Triple prime, 2x to the negative 3, which is the same as 2 factorial. So f4 of x, negative 3 factorial x to the negative 4. f5 of x is 4 factorial x to the negative 5. And then we have f of 1, f prime of 1, f prime 1, f4 prime 1, f5 prime 1. Okay, and evaluate all those critters. And you'll get 0, 1, negative 1, 2 factorial, negative 3 factorial, and then 4 factorial. Okay. Okay, and then we just tack that into our formula for the Maclaurens and the Taylor series. You probably want that out for reference for the test, so you're not strapped for time when the time comes. So this will be 0 plus 1x times minus 1. So it's a Taylor series. So you have x minus 1 squared, etc. Then minus 1 all over 2 times x minus 1 squared. And then plus 2 factorial all over 3 factorial times x minus 1 cubed. Minus 3 factorial over 4 factorial times x minus 1 to the 4th, plus 4 factorial over 5 factorial times x minus 1 to the 5th, plus everything. Yeah, it goes on forever. So you need a dot, dot, dot there, please. Then you can simplify it, hopefully a little bit. Not much to do, really. 2 factorial over 3 factorial is the same as 1/3. Whoops, I did not mean to put an equal sign there. So this, and then minus 1/4. Oops, oh gosh. So this would be x minus 1 cubed minus 1/4 times x minus 1 to the 4th plus 1/5 times x minus 1 to the 5th plus dot, dot, dot. And there she is. Okay. What I want to do with this then is to use the series to compute, and you see examples of this on my on last year's tests. So I want you to get a 4-term approximation of the integral. And you could use your table of integrals, or sorry, table of Maclaurin series to figure out the Maclaurin series, in this case, number 65. Integral from 0 to 1 of sine of x all over x dx. Okay. So this is the integral from 0 to 1. Sine of x is odd, right? So it'd be x minus x cubed over 3 factorial, and how many terms? We need 4. So x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. And of course, that's all over just plain old x. So we can simplify that. So it would be 0 to 1 of 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th 7 factorial plus dot, dot, dot. Dx. Then I need to integrate that. So I have x minus x cubed over 3 times 3 factorial plus x to the 5th over 5 times 5 factorial minus x to the 7th over 7 times 7 factorial plus dot, dot, dot. And I have to evaluate from 0 to 1. Okay. And when you plug in 0, everything will just be 0. So all you're really doing is plugging in 1, and we only want the first 4 terms. Okay. I'm not going to expect you to, make sure your approximation is within 0.0001 of the actual value. All I need you to do is find the first 4 terms. Okay. So kind of not as hard. So what you'll have is this thing. I don't have a calculator on me, so I'm not going to be able to get the actual value like you will on the test. Okay. But I should at least see this value, and then you'll have, your decimal approximation for your answer. Okay. Okay, so hopefully that is a very comprehensive look at what to expect on the test. So it'll be very similar to that. I expect you to show work. If you do not show work, you are in trouble. I will give you a very bad grade. Okay. There is plenty of work to show. I expect that if you are doing all this in your head, you should probably go to MIT and not to Tri-C. Not that Tri-C isn't good for some people. I've had some very smart people come here just because, it's a very small college as compared to somewhere where you have 1,000 people per class. Well, 100 people per class, right? So anyways, there's all that junk. I'm babbling on. Okay, I'll leave it at that. We'll see you next time. Okay, bye-bye.